Okay.
So welcome to the Inverse Problems seminar. So we are happy today to have John Schotland, which will be talking about two interesting topics, quantum optics and random media. So thank you, John.
Okay. Thank you very much, Knut. So I just want to verify you can see my screen and the pointer. Is that correct?
Yeah, we see it. We see it well.
Okay. Great. I should begin with a disclaimer, which is that I'm not an expert at Zoom, and this is the first time I have ever shared my screen with anyone. So anyway, thank you very much for the invitation, and also for organizing the seminar series. It's been a great service to the community, and I look forward, every Thursday to attending. I've missed only a couple. Fortunately, not this one. So anyway, this talk is about a long-term project on quantum optics in complex media. And it might not seem necessarily that it's so closely connected to the nominal topic of inverse problems, but which is the purpose of this seminar series, but I'll try to make the case for it in a little while. And so I'll begin by saying that I've made a living working on problems in classical optics and related inverse problems for a long time now. And implicit in that work has always been the assumption that light behaves like a classical field. And so I began now a while ago asking myself the question, are quantum states of light of any use for imaging? Are there any advantages to be had? And I should say that I don't know the answer to this question, but I am developing tools, and some of these tools have taken a bit of time away from the basic question of imaging itself, and you'll see how this plays out. Okay, so I'll begin with an experiment that recalls many of the physical ideas in the classical setting. And so before I do that, let me say that all of the work I'm going to talk about today is joint with my graduate student, Joe Chrysler, who just defended his PhD thesis this week. And so this is the second talk of this kind that I've heard about. So let me see if I can expand the screen fully. And Knut, I just want to verify that you can again see the slides and my pointer, huh?
Yeah, it looks so good. It looks good, John.
Okay, thanks. Okay, so here's the experiment. And this experiment was actually done with one of my kids when she was about 8 years old. And now she's 20 or so. So it has stood the test of time. We did it in our kitchen as a school project. And the ingredients are very simple. So it's just a glass. We called it a beaker. And there's a laser pointer. There's some water in the glass. And you can see that the laser pointer is turned on because its reflection is present against the back wall of the container. Then we add a little bit of milk, which causes the beam to scatter. Not so much, so the trajectory is largely linear. And then you add more milk, and with more scattering occurring, until eventually there is so much scattering that the beam diffuses. Okay. So there's a lot of physics in this picture. And most of it can be explained by the so-called radiative transport equation or radiative transport theory. So this is a rather powerful model that describes the propagation of light in disordered media in terms of a physical quantity called the specific intensity. So it depends on a point in space, a direction, and a time. So roughly speaking, you could think of it as the intensity of light in this phase space of points, directions, and time. So The radiative transport equation I've written here, and it's a kinetic equation that expresses the conservation of gains and losses of the specific intensity due to scattering. So on the left-hand side, there is a transport term, and on the right-hand side are the gains and losses. This term here expresses the change in direction, if you will, of a ray from one ingoing direction k prime to an outgoing direction k, integrated all over the possible outgoing directions. And this function here is called the phase function, and it's normalized so that its integral is 1 for all possible outgoing directions. Okay. So this is the beast, the radiative transport equation, and it's been around for a long time. It was first written down phenomenologically around 1900 as a way of describing the propagation of light in interstellar media, and since then has had many applications, most prominently, I suppose, in the last 15 years or so, to biomedical optics, where there is great interest in the study of light propagation in tissue. The equation it can be thought of in some senses as like a linearized version of the Boltzmann equation from the kinetic theory of gases, except that there are no interactions between the particles. Right? The particles here you can sort of think of as the light rays, and they interact only with the medium. Okay, so at large distances and long times, it turns out that the solution to this radiative transport equation is well approximated by diffusion. And you can relate the specific intensity to the so-called energy density, which is just an angular integral of the specific intensity plus the first order correction, so a gradient. And here the diffusion coefficient is, excuse me, I'm getting a phone call. I'm not an expert. Let me see if I can figure out how to turn that off. Now I have lost the call. Knut, are you still there?
Yeah, I'm here.
I can't see my screen at the moment.
Okay, actually we can see it here, so.
Yeah, but that's not going to help me.
No?
Well, I can't see it. So, yeah, hold on. Sorry about the technical difficulty. I'm going to stop I'm going to stop the screen sharing,
Yeah.
and see if it recovers. Where is the preview? Okay, can you guys see this?
Not yet, no.
Okay, so let me try to resume screen sharing. I'm going to share the whole desktop.
Yeah. Yeah, no, we're almost there.
And now can you see it?
No, it's perfect again. Yeah, looks good.
Okay, great. Sorry about that. Yeah, so actually, Knut, if you wouldn't mind leaving your video on, it helps me to have at least one person I'm talking to.
Exactly, yeah.
Yeah, and what we do in quantum optics. Okay, now I'm having trouble advancing my slides. Sorry. Okay, so the motivation then for today's talk is the idea that the radiative transport theory of light is based on classical theories of light propagation. And so the questions we want to answer are, namely, are there quantum effects which are important in light scattering, especially multiple light scattering? And to think about this, we will study two cases. So the first is spontaneous emission in random media. I'll explain what these words mean in a few minutes. And the second is the transport of entangled states of light, so some important non-classical states of light. Okay, and the second topic especially has applications to both imaging and communications. Okay, so I'd now like to give a kind of crash course in quantum optics, tell you everything you need to know to understand, I hope, the rest of the talk. So this is really a subject which deals with the quantum theory of the interaction of light and matter, which is to say that it is necessary here to treat both the electromagnetic field and the matter with which it interacts at a fully quantum mechanical level. There are theories in which the light is treated classically and the matter is quantized. And those things apply very well to situations in which there are a large number of photons. But in the problems that we're going to be discussing, in which there are only one or two, it's necessary to think about a fully quantum theory. Okay, so why quantum optics? Well, there are two main reasons. The first is that there are phenomena which cannot be properly explained by classical physics. And in particular, there are non-classical states of light. You may have heard about squeeze states, and you may also have heard about entanglement, which is a kind of correlation of quantum fields, which is not present classically. Okay. Now, the subject has a long history, and in fact goes back to the early days of quantum electrodynamics, but only became important after the development of the laser in the early 1960s. And this was because at that time it was possible to really obtain sources of light in which quantum effects could be easily achieved and matter could be manipulated accordingly. So the subject is closely tied to experiment, and it's only a slight exaggeration to say that it is primarily concerned with one atom interacting with one photon. Now, in the past decade or so, experiments have improved, and it is now possible to study more than one photon, particularly entangled states, and systems with larger numbers of atoms. The trouble is, from a sort of mathematical or theoretical perspective, that the mathematical tools have not really kept up, and that the many atom problems that one would like to study are somehow exponentially hard. That is to say, they cost an exponentially number of operations in the number of atoms in the problem. Okay. So as I've said, the talk will really have several parts. We'll begin with a crash course in quantum optics. Then I'll introduce some new mathematical tools for many-body problems. And these are primarily problems involving large numbers of atoms and variable numbers of photons. The two key ideas are that we will need a sort of real space formulation of quantum electrodynamics. Again, I'll say something about what that means in just a few minutes. And we will also make use in this real space setting of PDEs with random coefficients. And then as case studies, I'll illustrate these ideas by studying the problem of spontaneous emission in random media and then transport of two-photon entangled states. Okay, so let me begin with a discussion about the quantization of the field. So classically, we might consider a scalar model of the electromagnetic field, that is to say, without accounting for polarization effects, in which case the field obeys a classical wave equation in vacuum. Now, let us suppose we expand the solution to this equation into Fourier modes in a box, so just plain waves, with some wave vector dependent coefficients. And then it's very easy to see that these coefficients, these UKs, which I'll sometimes refer to as modes, satisfy the equation mode by mode for a harmonic oscillator. Okay. And so this corresponds to independent harmonic oscillator modes with frequencies omega k, which are simply proportional to the wave number. Okay. So at this stage, we haven't done anything except explain something which I think probably everybody already knows, which is that you can look at waves mode by mode, okay, and the waves and the modes behave independently. Now, when one wants to go ahead and create a quantum mechanical description of this phenomenon, the way to do this is to quantize the oscillators by promoting these modes, these UKs, to operators, and we do this in the usual way. Okay, and so then we have a whole collection of quantized oscillators, one for each mode of the field, right? And so the Hamiltonian then just looks like a Hamiltonian for a whole collection of oscillators. And here h bar omega k is the energy of one mode, and ak dagger ak is the number operator for that mode, and then we simply sum over all of the modes. Okay, so the creation and annihilation operators for each mode act on the number states. So the creation operator simply increases the occupation number of a state by 1, and the annihilation operator decreases the occupation number by 1. And the normalizations are set up in such a way that the commutation relations, which I've written here, are obeyed. So what this says is that the photons in the mode, which are sort of collective excitations of the field, obey bosonic commutation relations, right? Okay, these behave like bosons. You can have as many particles as you like, as many excitations as you like in a mode, okay, from 0 to infinity. Okay, so that's the idea of the quantization of the field. It gets described purely in terms of these wave number modes. There is one photon label for each mode, and the modes, I say, are just these sort of collective excitations of the whole field. So if you have seen the quantization of the harmonic oscillator in quantum mechanics, we just do this over and over and over again for every mode. Okay, now, what about the matter in the problem? So we're going to make life as simple as possible, and we're going to think about atoms which don't move and which have a ground state and an excited state. So these are so-called two-level atoms. And there is an energy gap between the ground and excited states. The energy here is just h bar capital omega. And the Hamiltonian for this system looks very much like the Hamiltonian for one oscillator, with a very important exception. So these raising and lowering operators, which excite and de-excite the atom, are not bosonic. They are fermionic, so they obey anti-commutation relations, okay? And the reason for this is because we can't continuously excite the atom. So if the atom is already in its excited state, then the application of one raising, of one lowering operator results in the atom making a transition to its ground state, but the application of a raising operator simply doesn't do anything at all, right? The atom is already excited. Okay, so this is why we can think of the atoms as fermions and the photons as bosons. Okay, so if the atom is initially in its excited state, and there is no interaction with the field whatsoever, if the system consists of simply one atom in the entire universe, then it will remain there forever. It's an eigenstate of the system, and although it may pick up a time-dependent phase, that's all that can happen. Okay, so how does the atom make a transition, for example, from its excited state to its ground state, or vice versa? So this arises, as you might imagine, because of the coupling of the atom to the electric field. So classically, the atom has an electric dipole moment, and it couples to the field bilinearly. So we have an interaction Hamiltonian which looks like a sum over modes. And we have this bilinear combination of the creation operator for mode K acting on the lowering operator for the atom, and then its Hermitian conjugate. Okay? The overall constant G here is some kind of coupling constant, which tells you the strength of the interaction, and it's just proportional to the dipole moment of the atom. Okay? So the first term here, you can say, corresponds to the loss of a photon by the atom and the gain of a photon by the field. Okay? And the second term is exactly the other way around. So now, if we think about an atom, which is in its excited state, then it turns out that the coupling to the field causes the atom to decay. And this process is referred to as spontaneous emission. Now, this can happen even when the field itself is in its ground state, which is to say it has no photons present at all. Okay? So this so-called vacuum field can drive the transition from the excited state of the atom to its ground state. And this is, as I say, why the emission is referred to as spontaneous. Okay. Now, so this is, roughly speaking, what happens with one atom. Suppose you consider a system of many identical two-level atoms. And for simplicity here, let's assume that the atoms are sufficiently well separated that we can ignore their interactions. So the only interactions in this problem are those between the atoms and the field. Okay? So now we can, in some sense, think about spontaneous emission again, but in what's called a collective form of spontaneous emission, also sometimes referred to as superradiance or subradiance. Okay, so spontaneous emission now, for example, if you start with a system in which the field is in its ground state or in the vacuum, and one atom, let us say, is in its excited state, then we can transfer the excitation from the atom to the field, from the field to other atoms, and so on. Okay, and if you start out without knowing exactly which of the atoms contains the excitation, then in fact the entire system of atoms can be said to be entangled. Okay. All right. So how do you describe such a thing? Well, the Hamiltonian for the system has three terms. It has the Hamiltonian of the field, it has the Hamiltonian of the atoms themselves, and then the interaction. So the field Hamiltonian is exactly what we saw before. It's just a sum of harmonic oscillator modes, each of which has an energy h bar omega k. The Hamiltonian of the atoms is, again, just a sum of all of the atoms, each of which is assumed to have the same transition frequency omega. The atoms here are labeled by J's. And the raising and lowering operators for the atoms obey the same anti-commutation relations that we saw before, which are written here. Okay. And now finally, the interaction Hamiltonian includes terms which are bilinear in both the atom and the field, and includes the positions of the atoms which are fixed at these points xj. So if we were to try to solve the Schrodinger equation, which corresponds to this Hamiltonian, let's suppose in the simplest possible case, where there are no excitations in the vacuum of the electromagnetic fields, that there are no photons present, but only one photon present one atom which is excited, then the number of equations that one would have to solve grows exponentially with the number of atoms. And so in experiments, this becomes a significant problem very quickly, as one could imagine. Okay, so we have to find some mathematical way of trying to deal with this. All right, so the idea, sort of maybe the most important idea in this talk, is that we want to do some kind of quantization of the field in real space. So, which is to say that we want to treat the atoms, which are somehow localized in space, and the electromagnetic field, which we find to be useful to talk about in terms of Fourier modes, on the same footing. And so to do this, we need to introduce a real space representation of the fields. So we're going to introduce an operator, phi of x, which is simply the Fourier transform of the lowering operator for the modes. Okay. Now, because the raising and lowering operators obey commutation relations, the field phi inherits those commutation relations and obeys bosonic commutation relations of the following form. Okay. And so if we try to, if we like then, in terms of these real space quantum fields, we can then rewrite the Fourier space Hamiltonian in the following way. So as you can see, we have essentially two copies of the field phi instead of two copies of the raising and lowering operators, okay? And then instead of h bar omega k, we have this operator which is the square root of the Laplacian. And this is easy to see because the square root of the Laplacian has the magnitude of the wave vector k as its Fourier multiplier. Okay? So this Hamiltonian, which we normally would write in Fourier space, can now be written in real space like this. Okay? And if we want to think about it in physical terms, then roughly speaking, we can think of phi dagger as an operator which creates a photon, to be careful about how you say all of this, at the point x, and phi annihilates a photon at the point x. Okay? It's really a little bit problematic physically, but mathematically there's no question that these two things are somehow equivalent. Okay, now the reason all of this is a little bit troublesome physically is because this square root of the Laplacian, this fractional Laplacian, is non-local. And so we'll define it by a Fourier integral. But in real space, you can see it has a nice representation as a principal value. Okay, so I don't want to attribute any real physical significance to the non-locality of this Hamiltonian. I mean, if you wake me up in the middle of the night and ask me, maybe I might be willing to say that, well, this has something to do with the fact that the photons are not perfectly localized and so forth. But I'm not entirely comfortable with this interpretation. Okay, so now we know how to treat the field in real space. We just introduce a scalar bosonic field. What about the atoms? Well, so I want to introduce a continuum model for the atomic degrees of freedom, which is to say that I'd like to have a number density rho. And then I simply integrate the number density against the Fermi fields, which raise and lower the excitations in the atoms, and give every atom the same resonance frequency capital omega. Okay, so obviously, if this simply consists of a sum of point masses, then we would recover the model that we have been dealing with before. But I'm going to be interested in random media, and in that situation, I'd like to think about rho as a random field. Okay. So this completely then defines the atomic Hamiltonian, and these are the corresponding anti-commutation relations for the raising and lowering operators for the atoms. Okay, and what about the Hamiltonian for the interaction? Well, it looks exactly like what you would expect. It's bilinear in the raising and lowering operators, which are for the atoms, and the field weighted by the density that we had before. Okay. So that's all we have. Okay, let me move on. How are we doing on time? Oh, good. So, all right. So the simplest problem to think about first is that of so-called one-photon states. Okay. So that's a situation in which the field has at most one photon present, and there can be up to one excitation in the atomic degrees of freedom. Okay. So the total Hamiltonian we will consider then consists of a sum of three terms, as always. So it's this non-local part which describes the field. This term here, which is purely fermionic and describes the atoms, and then this term here, which is the interaction term, which is bilinear in both. Okay. So so now we want to think about a so-called one-photon state. So that's the state psi. And how do we create such a state? Well, we consider the vacuum a state of both the field and the atoms. So there are no excitations and no photons present. And then we can create a photon, one photon, by letting the operator phi dagger act on the vacuum. And we weight this with a probability amplitude psi, which is the so-called one-photon amplitude. And likewise, we can create an excitation in the atomic degrees of freedom at the point x with an amplitude a, weighted by the appropriate density, okay? And the most general state that we consider then that's consistent with the Hamiltonian is a linear combination of such states, okay? So anyway, so A is the probability amplitude for exciting an atom at the point x, and psi, if you like, is the amplitude for creating a photon at the point x in time t, okay? And then the amplitudes have to obey a normalization condition, which you can think of as a sort of conservation of probability for the whole system. Now, the one photon state, it's the state of the system, obeys the Schrodinger equation, right? So it tells you how it evolves in terms of the Hamiltonian H that includes the contributions from the field and the atoms and their interactions, okay? So what you can then ask is, given the Schrodinger equation and the form of the state, what are the equations which are obeyed by the amplitudes for the atom and for the field itself, okay? And so these are simply determined from those two ingredients that I just mentioned, and they look like this. So they're sort of pseudo-differential, right? The fractional Laplacian appears in the field for the field psi, for the amplitude of the field. Rho here is the density that we're interested in. G is a constant. And then the time evolution of the amplitude is simply given by an ODE. Okay? In some sense, that's because the atoms in this problem don't move. All right, so if we can solve this system of PDEs, which are sort of maybe the most important result in this talk for the one photon problem, then we can understand how psi and A evolve in time, and this tells us the state of the system, and once we know the state of the system, we can compute any observable we're interested in, okay? All right, so the simplest problem you might think of studying is that which corresponds to just a single atom, right? And this would mean that rho here is just concentrated at a point. So if we take rho to correspond to a single atom at the origin, so it's a little delta, and we assume that the atom is initially in its excited state and that there are no photons present in the field, and we are describing this basic process of spontaneous emission, then turns out we can solve these equations, and we find that the probability that the atom remains in its excited state decays exponentially at long times, okay? So we solve for A, we square it up, and this is what we get. And gamma here, which is the rate of decay, simply depends on the strength of the coupling and the transition frequency. Okay. All right, now, as you could imagine, this is an old problem, and this result that we get agrees with classical results of Wigner and Weisskopf, which were obtained in the 1930s. And so, importantly, they didn't solve this problem the way I've just shown to you. That is to say, they did not take a PDE point of view, right? They wrote down some states, they solved some linear equations, and they obtained this result. So it's reassuring that we can get the same answer that they got, but that's really not, of course, enough. Let me also point out that we can also solve for psi, which is the one photon probability density. And when we do this, we simply find that we get a Lorentzian spectral line, as you might expect, and it involves the so-called Lamb shift, which is a number that has to be properly calculated and in fact diverges, so has to be renormalized. And the key point here is that we get exactly what we would expect to get for a point scatter or a small scatter whose size is small compared to the wavelength of light in classical optics. Okay, so this is the result you would expect to get classically. Of course, we've given a quantum mechanical interpretation to the line width and the frequency shift and so on. But what we get is roughly speaking consistent with what you would expect in classical optics. So no surprises. Okay. So now let's talk about what happens in random media. Okay. So in a random medium, what we would like to understand are the expectations of these probabilities, right? A squared and psi squared. And here, this is a statistical averaging over the random medium. Okay. So we take the random field rho to be composed of a term which is constant. So you can think of this as a constant background plus a correction. And this correction, which represents, of course, the density fluctuations in the field, we take to be statistically homogeneous and isotropic. So it has zero mean, and it has correlations which are prescribed in the following way. Okay. So how do we get our hands on these two quantities? So to do so, we're going to follow many of the same ideas that one needs to study problems of wave propagation in random media, but they have to be adapted to this setting of quantum optics. And so roughly, the way this works is that we observe that the solutions to these equations, the amplitudes A and psi, oscillate rapidly on the scale of the wavelength. And we'd like to understand the high frequency asymptotics of this system, where the propagation distance is long compared to the wavelength, and the propagation time is large compared to the period of oscillation, and the density rho is slowly varying. Okay. So suppose we introduce, as you might expect, slow space and time coordinates. So that is to say, we rescale space and time by a small parameter epsilon, and then we consider a high frequency limit in which epsilon goes to 0. Okay. So if we introduce rescaled amplitudes, A sub epsilon and psi sub epsilon, then they satisfy the system of PDEs that we saw earlier. But we have to make a small change, which is that we also need to rescale the density fluctuations in such a way that the randomness is sufficiently weak that the correlations are of order epsilon. Okay. So this high frequency weak disorder regime is exactly the setting in which you get radiative transport theory for classical wave fields. Okay. So if we had studied, let's say, the Schrodinger equation or the Maxwell equations or something else in this high frequency scaling regime, then we might expect to get radiative transport. The question is, what do we get in quantum optics? Okay. All right. So the way one answers these kinds of questions is to introduce the Wigner transform, which is a kind of phase space probability distribution. And so this is what it looks like. So in this case, we have two fields, so we make a vector out of them, which is capital U. And then we shift to relative and center of mass coordinates and Fourier transform with respect to the shifted coordinate. And we get this phase space quantity, which depends upon position and the wave vector k and time. Okay. Now, what's interesting about this Wigner transform is that we can obtain the probability densities that we're interested in simply from angular moments, from the lowest order angular moments of the Wigner transform. Okay. Moreover, the diagonal elements, which we are interested in here, are real valued, but not necessarily non-negative. This is a sort of well-known pathology of the Wigner transform. However, in the high frequency limit, as epsilon goes to 0, it will turn out that W, in fact, does become non-negative. Okay. All right. So that's the Wigner transform. And so what do we do with it? Well, we want to find the equations that it satisfies on average. So what we do is we decompose sort of lowest order part of the Wigner transform into modes, which we call A plus and A minus, with coefficients A plus and A minus. And these modes are of course time dependent. And it can be shown that in the high frequency limit, that these modes obey a kinetic equation which looks just like the classical radiative transport equation in classical optics. Now, what are the differences here? Well, the differences are that this coefficient sigma plus or minus and this so-called phase function here depend upon the parameters in the quantum optical problem, which is to say the background density, the coupling, the transition frequency, and so on. And the phase function A is related to the density correlations. How do you get such a result? Well, this is a long story, okay? But once you have it, of course, you can then construct the solutions, for example, by the diffusion approximation, and once one has those, construct the Wigner transform, compute its moments, and get the things you're interested in. Okay, so what are the key ingredients in this long story? Well, the first thing to notice is that the Wigner transform obeys an evolution equation in terms of an operator L, whose form I don't need right now, but which depends upon the random field eta. Okay. Then in order to extract the high frequency limit, we introduce a multi-scale expansion for the Wigner transform in powers of the square root of epsilon. Okay. And we introduce a corresponding variable capital X, which is fast. And we make the assumption that the term W0 here is deterministic. Okay, so it doesn't depend, in particular, it also doesn't depend on the fast variable X. Okay. So then by separating terms of order 1, order square root of epsilon, and so on, we can obtain a hierarchy of equations, which can then be averaged over the random field eta. And by suitably closing them, we get the required kinetic equation that I've written here. Okay. Okay, so that's a long story. So what do you do with all of this? Well, so let's consider the simplest problem we possibly could in this setting, which is spontaneous emission. So this is in a random medium now. So let's suppose that we have a collection of atoms which are initially excited in some volume of linear dimension Ls. And so this corresponds to an initial amplitude of the atoms, which is Gaussian with some width. And let's suppose that there are no photons present in the field. So the field amplitude, the one photon amplitude of the field vanishes. Okay. Then we can solve the corresponding diffusion equations, which correspond to those kinetic equations for an infinite medium. We take some reasonable choices of the physical parameters, and we can write down solutions to these equations. Now, at long times, it turns out that these solutions simply decay algebraically in time with corrections that one can compute explicitly. And if you actually plot the solutions, these are the probability amplitudes squared, right? These are probability densities, if you like. Then this is what you get, okay? So this is the time dependence of the corresponding probability distributions, psi squared and a squared. And what you see is that they decay in time, but they are not always non-negative, right? And so this is due to the breakdown, if you will, of the diffusion approximation at short times and short distances. But at longer times, we recover the positive nature of the solutions. Okay, so there is a trade-off then between the excitations of the atom and the field, and this is how they behave. All right, so this is spontaneous emission from a locally excited collection of atoms. Okay, so that's our sort of first physical result. Now, what happens if we now think about a situation which is really manifestly quantum mechanical? And that is, what happens if we have a two-photon state of the system, okay? So we have the same Hamiltonian with the terms that involve the field, the atoms, and their interaction. But now we think about a two-photon state, okay? So this means that this term here allows for two excitations of the field. So that is to say, we can have a photon at the point x1 and another photon at the point x2. This term here allows for two excitations of the atoms. Actually, there should be another factor of the atomic density here. No, I'm sorry, I'm actually looking at the wrong term. This term here allows for two excitations of the atoms. So one atom is excited here at x1, and the second atom is excited here at x2, and there are two corresponding factors of the density. And this term here allows for one excitation of a photon at x1 and one excitation of an atom at x2. So in the entire system, there are at most two excitations of any kind which are present at one time. Okay, so then A here is the amplitude for exciting two atoms. Psi2 is the amplitude for exciting two photons, and Psi1 is the amplitude for jointly exciting an atom and creating a photon. Now, the amplitude A, because it describes two atoms and the atoms are fermionic, has to be antisymmetric under interchange of its position arguments x1 and x2. And the amplitude Psi2, because it is describing a Bose field, is symmetric under exchange. Okay, there's no such symmetry of Psi1. Okay, now the important physical point here is that there can be entanglement of the photons in the system, which means that this amplitude Psi2 does not factorize. So it's a kind of lack of independence, if you will. And likewise, the atoms can be entangled. Again, this thing might not factorize. And a photon can be entangled with the atoms. So again, this quantity Psi1 may not factorize. Okay. So this is a purely quantum mechanical effect that we are talking about. I'm not aware of any classical analog of this kind of entanglement. Okay. Now, the dynamics of this system, of this state, is again governed by the Schrodinger equation. And we can ask, what are the equations that are obeyed by the amplitudes, right? The amplitude A, Psi1, and Psi2. So once again, we got a system of coupled pseudo-differential equations. We get two appearances of the fractional Laplacian in Psi2. So this is kind of like a two-particle equation. One appearance of the fractional Laplacian in Psi1, corresponding to the photon. And an ODE for the amplitude A. Okay, and I've also introduced here a kind of symmetrized quantity Psi1 tilde, which allows us to deal with a completely symmetric system of equations, 4 PDEs instead of 3. Okay, now you can ask, as before, what happens if we allow for only a single atom and assume that the atom is in its excited state? Okay. And we have one photon in the field. So how does this differ from spontaneous emission, where there was only a single atom in its excited state and no atoms in the field? Okay. So this is what's referred to as stimulated emission. And in this case, you get a modification of the exponential decay of the population of the excited state. And this process of stimulated emission, which I'm not going to talk about anymore, is again, it's a fundamental process in quantum optics. All right, and in the right circumstances leads to the phenomenon of lasing. Okay, so what about random media? Well, it turns out in a random medium, one can ask many of the same questions that we asked in the case of a single photon. We can construct a Wigner transform, which is now a Wigner transform of all of these fields, Psi1, Psi2, A, and in fact, this symmetrized version of Psi1 as well. And we can look at its high frequency limit, its asymptotics, and so on. We can diagonalize the modes. And then each of these modes, there are now 4 of them, which contain two copies of the spatial coordinates and 2 copies of these wave vectors, obey kinetic equations, where these coefficients, again, depend on the parameters of the problem, and this transport operator is related to density correlations. Okay, so this looks just like a radiative transport equation, except that it's kind of a radiative transport equation or a kinetic equation for 2 particles rather than 1. Okay, so it's like a Boltzmann equation for 2 particles, which can interact with the medium in which they are moving, but not with each other. It's still linear. And it turns out it's possible to construct a diffusion approximation for this two-particle kinetic equation in the standard way. And if you do this, you can solve the equations. Now, suppose that there are two photons which are present in the field, and that the atoms are initially in their ground states. Okay, so this means that the atomic amplitude vanishes, the cross amplitude psi1 also vanishes, and the amplitude psi2 will take to have the following form. So again, it looks like two localized little bumps. Okay, but they have to be symmetrized in order to make psi2 symmetric. And you can see that this corresponds to an entangled state of the system, right? This function psi2 is not separable. You can't write it as the product of a function of x1 and a function of x2 alone. Okay. So now you can ask, what happens to the entanglement of the whole system as it evolves in time? Do the atoms become entangled? Do the photons psi2 remain entangled? Is there entanglement of the atoms with the photons and so on? Okay. So to answer questions like this, we can solve these kinetic equations. And the details here are a little bit long. So I'll just show you some numerical results. But again, you can plot the probability distributions for the two photons. That's this guy here. You can plot the probability distribution for the atoms. That's this guy here. And this is the cross one. They should be drawn differently. I can't remember which is which. I think this is psi1. They're both negative at short times, but at long times, they become positive and decay. Okay. And so again, this represents the trade-off of the spontaneous emission, the stimulated emission, and so on from the atoms with the field. Okay. Okay, so let me draw some conclusions. So what we've seen is that many body problems in quantum optics are mathematically challenging. In the conventional formulation of quantum optics, the computational cost grows exponentially with the number of atoms. And this is more than a technical problem. It's really a problem of principle. And it's a problem that requires the development of new mathematical tools to overcome it. And so what we've tried to suggest in this talk is that one way to approach this is to introduce a kind of real space quantization procedure, which in random media leads to the study of PDEs, in fact, pseudo-differential equations with random coefficients. And then by applying the usual kind of machinery, which is known to people who work in the subject of classical waves in random media, we can develop kinetic equations that describe both one and two photon processes. We've applied these ideas to study both spontaneous emission, which is a one-photon process, and the transport of an entangled two-photon pair, again, both in random media. Okay. As you might imagine, there are a number of open problems that one can consider some of which I understand a little bit about, but which we don't have time to really discuss. So one question might be, well, is there a way to measure the entanglement of the photons? So you say, well, is there a quantitative way to express how entangled they are initially and how entangled they become at long times? And likewise, are there ways to describe the gain of entanglement of the atoms or the mixed field psi1? Okay. Another question, which is something that sort of motivated all of this to begin with, is, are there reasons to try and do imaging with entangled two-photon states? So you could imagine experiments which are sort of akin to ghost imaging, in which one takes a pair of entangled photons, sends one of the photons through a medium of interest, collects all of the light that comes out, and sends the other one to a sort of spatially resolved detector. And then you can ask, well, is it possible to image this way? can you find the coefficients in the non-local PDEs that we've seen? Now, this problem is a bit different than the usual problem of ghost imaging for partially coherent light, because in practice, detectors here don't provide us with phase information. We have to look at a problem in which we have no phases, in which we can only measure a squared and psi squared. So we want to solve a kind of phaseless inverse problem for a pair, let's say, of well, for this set of equations right here. Okay, so this is actually 3 equations. So we want to know, if we measure psi2, can we recover rho? Well, we can't really measure psi2, so we can measure psi squared. Could we recover rho? Okay. Another question is that of localization. So if the disorder is not weak, which is what we've needed to assume in order to obtain transport equations, then you might ask, can light be trapped? Now, if this were a Schrodinger equation rather than an equation with the square root of the Laplacian, then quite a lot is known about this. In the case of the square root of the Laplacian, we have some results for both the one-photon and two-photon cases for an analogous problem on a lattice. That is to say, where the Laplacian is replaced by the graph Laplacian on, let's say, a 3-dimensional square lattice, 3-dimensional cubic lattice. We don't know what happens in the continuum. And then finally, are there, what is the theory of resonances for an operator like this? Evidently, we do have resonances. That's what the spontaneous decay and well, the resonant one-photon amplitude that I showed you earlier is indicating. But we don't really understand very much about this problem, and we don't understand anything about it really in the two-photon case. Okay, thank you very much. I think I'll stop.
Thanks, John, for a very, very nice talk.
I'm going to stop sharing.
Yeah. Good. So now, any questions for John? Please unmute yourself.
Thank you. Yeah, I do have maybe 1 or 2 questions.
Sure.
Yeah. So it's about the intent. So this, I don't know how parallel is your approach to operator algebraic approach, but I was aware of the work of William Arveston of quantifying the entangled states, and it in an infinite dimensional function space. So there was like a way of measuring how entangled, like formally, things are, but that was more in the context of operator algebras, CSR algebras. Maybe like, I don't know how you have a translation to that language in your perspective.
Yeah, so it's an excellent question. I wish I could answer it. I'm afraid that C-star algebras and these kinds of things are above my pay grade. I know the name of the person you were mentioning. He has a book on C-star algebras that I unsuccessfully tried to read when I was a graduate student. So let me, if I could answer a question with a question. So in what context is he thinking about entanglement?
Tensor product of Hilbert spaces,
yes.
Multiple quantum systems,
yes.
And then you, yeah.
So he's thinking about entanglement perhaps of particles rather than modes of a quantum field theory. Is that right?
I think it's like mathematically defined based on the structure of a Hilbert space. More mathematics than physics.
So all right. So there is a Hilbert space, of course, running around here. In the two-photon problem, there's a sort of a sector of that Hilbert space which contains only the two-photon excitations. If you can view this as a factorization, then you don't have any entanglement. And so this corresponds to the statement that, let's say, the wave function psi factorizes as a product. Okay, it's a kind of independence. Now, I have no idea what the connection to C-star algebras is. Now, you can ask, for this problem, how could you measure the entanglement of let's say, a two-photon state? So one way of thinking about this is to regard this two-photon state as an operator, as defining an operator. And then that operator on that Hilbert space you were mentioning earlier has a singular value decomposition. If there is only sort of one term in that singular value decomposition, then the state is not entangled.
Yes.
If there are many terms, it becomes entangled. Then a measure of the entanglement, you have to boil this very complicated object down to some number. So one way to do this is to compute an entropy from the singular values. And then from this, you can get a number, which is the entanglement. We've looked at this kind of thing. And you can show, for example, that if you start off with a state which isn't entangled, then you cannot create entanglement. You can also start off with states that are entangled, and then the entanglement can evolve, meaning that the entanglement entropy can change.
Yeah. Thank you.
Sure.
John, I have a question.
Oh, Michael.
Hi, how are you doing? So let's see, in the two-photon problem.
Yeah.
Let's see, so you have both spontaneous emission and stimulated emission.
Yes.
Are those decay rates, are they transient exponentials, just as in the one-photon, one-atom case?
So, yes. So if they are, so let me understand. So in the case of, you're asking me about, let's say, one atom, but with two photons or two excitations in the system. Is that right?
Right. So
in that case, you can work out the full theory here, of course, just as you could for the case of the Wigner-Weisskopf theory of spontaneous emission. And then you get exponentially small rates of decay. Now, in the case of a random medium, well, you get solutions to these diffusion equations. So if the medium is statistically homogeneous and isotropic, then there is an overall exponential decay in time.
So in the random problem, do you think you have resonances as well?
I don't know. I would imagine so, but I don't even know quite how to answer the question or how to think about the question.
Okay. And a second question is, so in experiments, you talked about experiments. So in experiments, typically, you do these in some kind of a finite cavity or something like that. What are the right boundary conditions to think about?
Oh, well. So, so if we are thinking about the transport equations themselves, then they are typical boundary conditions for transport equations, sort of one-way boundary conditions. If we are thinking about the pseudo-differential equations, then I don't know the answer to this question. So if there was a jump condition, for example, suppose you had an object that was homogeneous and you try to describe what's happening inside and outside of the object, then somehow this has to respect the non-locality of the operators. There are people who have thought about these kinds of things in other contexts, but I don't know the answer to this question. And in particular, I don't know what the analog of radiation conditions would be, even in the case of an infinite medium. Even in 1D.
I mean, for the non-local problem,
Yeah,
I guess some kind of projection onto outgoing waves.
I guess, but
Mhm.
I want to be slightly careful.
Mhm.
Privately, I might say something else.
Thank you.
Sure.
I am Dima Jacobson from Montreal. Wanted to ask, is there a connection to Ising model and Potts model and things like that?
Not that I know of. Where would I find such a thing?
Oh, I don't know, maybe some overview, but you mentioned that you were looking at some problems on a lattice, right?
I see. Yes. So no, not quite like this.
Okay.
I think of those problems as sort of purely combinatorial and not involving any external fields except perhaps classical fields.
I see. But is there a good reference for problems on a lattice that
No, I don't know of such a reference. I mean, there are certainly problems about localization on lattices.
right. But you think they're different, right? Or
I'm not sure that they're different. What I know is that the tools that seem to work on lattices are not so easy to extend to the continuum.
I see.
There are real experts on this. I'm not one of them.
I see. And I guess another was just a small remark that like half integer powers of Laplacian, they come up in some problems in conformal geometry. And I think there is some work of, Caffarelli and other people reasonably recently, which sort of, if you go one dimension up, they become local or something like that.
Yeah. So
so I'm not sure if this is useful at all, but
I don't know. The work of Caffarelli and this is Silvestri, is that right?
Could be, yes, I think
yeah.
so.
I have to look into this.
Yeah, that's just.
We don't know the most basic things about this system of equations. And as Michael says, what are the right boundary conditions? What are the right spaces in which to think about all of this? What I've shown you are really the results of formal calculations.
Thank you.
You're welcome.
So any further questions for John? So I was wondering, John, so these are applications to biomedical imaging,
Yes.
in two-photon imaging, for instance. So any connections to your framework here?
I hope so.
Yeah.
But I don't know.
Okay.
I mean, let me say it like this. The two-photon imaging that I know of, this is somehow, there's no quantum mechanics that's really needed to describe any of that. But there are certainly, one could imagine two-photon processes that could be useful for microscopic imaging, where this kind of entanglement could be used, for example, to increase the signal to noise.
Mm-hmm.
I believe that this is the main advantage of things like ghost imaging. You don't really get any improvement in resolution.
Mm.
And the quantum and classical effects in many instances are really just about the same.
Right. So what will determine the signal to noise ratio then?
Yeah, it's possible. That would be the place to look. I mean, you know, roughly speaking, you have twice the number of counts. So you should get a square root of 2.
And so if you really increase the number of photons, make it very, very large, then you get sort of back to classical. So
Yeah, exactly. Then you're back in the classical setting. And so you might say, well, why bother with all of this?
And so if you have, I don't know, some sort of intermediate number of photons, I don't know, 20,
Well,
50 or something. So
yeah, well, then who knows? Let me perhaps say something a little bit different then. So in communications, there are protocols in which people explicitly make use of two photons that are entangled. And the theory for such things is wonderful as long as you don't take into account the interactions of the photons with the environment so that you lose coherence. So if you want to ask, for example, what is the sort of channel capacity for a two-photon communication experiment of a certain kind, then this is a difficult question to answer, except in the ideal situation where you don't have any coherent, when you have perfectly coherent light.
So is it related to the things people work on in quantum computing, like decoherence and so on?
Yeah, so it's the same process. So but it's a little bit weird because in quantum computing, decoherence is your enemy.
Mm-hmm.
And here, in some ways, decoherence is your friend. Without decoherence, you wouldn't be able to interact with the system.
Okay.
So I'll say something else then, which is that you know, there's this so-called second quantum revolution, in which people are trying to do all kinds of things to exploit non-classical states of light, of matter, and so forth. Much of it has to do with quantum computing, but there's a parallel strand which has to do with quantum measurements, trying to improve signal to noise in various ways. And here the argument that people make is that actually it's the decoherence you care about.
So let me ask one. Yeah, sorry. So let's going to ask one more question because you mentioned it. So what you're doing is on a scalar field.
Yes.
And that's the assumption, at least.
Mm-hmm.
If we think of some sort of vector field, then even the problem of localization, you might use Dirac operator for square root of Laplacian. You get rid of the localization as like a bonus or something.
Right. So it's a good question as to how to handle the polarization properly. I mean, the simplest way to do it would be would be not to introduce spinors, but just to leave a polarization label on the fields. In which case, the theory still remains non-local. I don't know what the physical meaning of the spinors would be here, right? You would need 4 of them or something like that. I don't think anything fundamental changes. On the other hand, you mentioned localization. So even classically, localization for vector fields is a kind of a hot topic. And the reason for this is because the Maxwell equations have a near field which decays as, you know, 1/r cubed. And there are indications from the numerics, particularly work of Sergei Petrov, that you don't get localization because of these near field effects. So I don't know what would happen in the quantum problem.
So any further remarks or questions for John? So curious, John, so for how also what is the so how do you deal with the fractional Laplacian and going to the transport equations?
So so are you asking me how do you find the evolution equation for the Wigner transform?
Yeah.
It's just a calculation. It's really, since it involves Fourier transforms, it's not particularly difficult.
Mm-hmm.
I should also say that for reasons that I don't actually know, Guillaume wrote a paper about radiative transport equations for sort of pseudo-differential type wave equations. I don't know if there was any physical motivation for this, but the construction that he used there is essentially the same.
Okay, right.
And in fact, it extends, to many different kinds of pseudo-differential operators, not just this,
Right.
this fractional Laplacian.
Yeah.
It's a, as you know, it's a purely formal thing.
So do you have access to any experiments in Yale, John, or any?
Don't even have access to my office most of the time.
That's right. Yes. Yeah, so,
but yeah, so Yale has a quantum institute, and it's one of the reasons I was interested in coming here. It's a major. Yale has a major program in quantum science, and right. It's one of the sort of pillars of their effort to build in the sciences.
Great.
And most of that has to do with quantum computing.
Yeah.
So there are opportunities.
Right. Good.
I should say these experiments are not easy to do. So I have a collaborator at Michigan who has been trying to do the sort of two-photon type experiments.
Yeah.
And so to get a two-photon source, which is bright enough, and whose sort of correlations, whose entanglement you can characterize, has taken a student that he has about 2 years to build. And in the end, it turned out to be very difficult to get it to be bright enough so that the detection had good enough statistics. And so the experiment that's actually being done involves only a relatively small number of modes, not all of the modes that one would have in a random medium like this. So it's challenging.
So what's next, John, for looking at problems in this direction? You're going in quantum computing, or?
No, I mean there are so many simple questions about just about these equations that, that we don't know. And I mean, certainly one thing that would be of great interest is to build solvers for them.
Right.
So there's some effort to do that now. But then we could try to understand, whether some of the results that we have are reasonable, because they're all, of course, based on formal calculations and uncontrolled approximations in some situations, like these closures, for example. So that's an area that needs some attention. Then, there's just the basic, then there are many questions that one could think about where there's no, where the medium is deterministic, but it's more, sort of more interesting than just a single atom. So an array of atoms. What is the homogenization theory for these kinds of things? What is the band structure? And what happens if one has for example, a two-dimensional lattice of these things, which is hexagonal? One question one can again ask is, are there edge states? Maybe Michael, this is something that I actually have been interested in discussing with Michael. If there are edge states, are they still robust? Hi, Michael. Any speculation?
Good question.
Yeah. So this is something I'm actually, we should talk about offline. I mean, even for a fractional Schrodinger equation, one could try to ask this question, I suppose.
One more question. So when you introduce the random medium, so how should one, is there a way of physically understanding sort of the spectrum, the correlation you have in the random medium?
Yeah. I didn't. You broke up.
So when you,
Knut, I didn't hear the question.
Right. So you introduce the random medium and a correlation structure in there. Is there a way to understand physically sort of what motivates the model?
So I think it's rather similar to what would happen in most problems like this. You could imagine you have a collection of atoms, and let's say for simplicity, they're relatively dilute, so that they don't overlap. Then you have kind of maybe an ideal gas or something with just very weak correlations. So in the right limit, that will look Gaussian. But as usual, we don't need this to be Gaussian. We just need the correlations.
Yeah.
Actually, this has always been a sort of a puzzle to me. If you look at the sort of diagrammatic approach to obtaining the radiative transport equation, the sort of physical approach, and I guess the work which has been done more rigorously by Erdos and Yao and so on. there they seem to require that the randomness really be Gaussian because they use Wick's theorem.
Mhm.
But in this asymptotic approach of, Riesick and Papanicolaou and Keller, they don't seem to require any such property. This is somehow all built into the closure. And I've never understood this.
Right.
It's one of these things where you do the calculation, you make the closure you need to make to get the answer you want to get.
Right. Yes, I guess the Gaussian is useful exactly to be able to push through that process.
Sorry?
Yeah, the Gaussian is useful to push through that process of the closure.
Yeah. It might be to justify that in some way. I don't know.
Yeah. Yeah. Well, okay, John, it was it's a great talk. I learned a lot. So last call if there are any more questions lurking around. But otherwise, let's thank the speaker once again. Again, I hope this is a start of a nice peer review at Yale and a lot of more interesting results in this direction.
Yeah. Thanks very much, Knut, and thank you for the invitation. I hope to see all of you in real life at some point.
Yeah, I hope